All right. Well, happy Monday. Happy week 10. It's June. It's last few days, I guess. Okay. Today, I don't know. It's just like a kind of just a side thing on PCA. Just showing you kind of like what dimension reduction kind of looks like, and it's a little bit I guess an application, although it's not like a very useful application in real life. This is we don't do things this way, but if you think about an image on the computer, okay, so here I've got this photograph. It's a black and white image from Ansel Adams, and if you think about it, it's just a whole bunch of pixels, right? And each of these pixels represents a value from usually like 0 to 255 to kind of indicate like how bright or how dim a pixel needs to be. And you can think of this. I don't remember what are the exact dimensions of this thing. It's 899 pixels wide, 720 pixels tall. Okay, so you can think of this as this very big matrix. What's 899 times 720? Around 650,000 ish values, and we can think of each column of pixels, right? You just think of like a data frame, and you can think of each of these 899 columns, columns of pixels as kind of like a column or a variable in your data set. And you can think of the 720 rows as like different observations or something. So, are some of these columns correlated? And if they are, can we reduce the dimensionality of our data? Okay, in that, like, if you think about it in an image, and this is like a completely random image, you imagine two columns of pixels next to each other would be fairly correlated, right? Because the column right next to this other column of pixels will probably look very similar. They're not all identical, because if all the columns were exactly the same, you would just have these horizontal stripes, right? But we don't have that. We have an image. So one column does change from the column next to it and stuff. But you imagine there's quite a bit of correlation between these two things. So anyway, what we're going to do is we're going to look at an image here, and we'll treat it like a big matrix, and then we'll see if we can do PCA to kind of reduce the, I guess, almost like a form of image compression, like reduce the amount of data that we have to transfer, and see if we can do this. So I'm going to use this package called Imager, and then and what I'm going to do is I'm going to take this this image, and I'm going to load it up. Okay. So Imager has this function load.image, and you just give it the name of some kind of image file, and it loads that up into the environment. So actually, let me clear this out. Okay. So here it says, it's this large thing with 647,000 things, and we can ask what are the dimensions, and it's 899 by 720 by 1 by 1. Okay. This is basically how many columns, how many rows. There are technically 3 color channels. Okay. A red, a green, and a blue, and then it supports kind of like GIFs, in that like you could have different frames. But basically, if you have a black and white image, which is what we have, the red, green, and blue values are all the same. So we're just going to kind of just reduce it. So I'm going to just get rid of these other kind of channels here, and then we will, and I will just kind of take this. So dimension of, we're going to have 720 rows, 899 columns, and then you can ask R to plot a matrix of values like this, okay? And so this is kind of what our image looks like right now. And if I take this matrix, and let's just look at the first 5 rows and the first 5 columns, okay? I guess we have values ranging from 0 to 1, okay? Where values close to 1 are bright white, and then values that are dark will be quite low. So if I, instead of, if we look at this lower left corner, so rows, I guess 700 through 720 or something, so I'll do just like 700 to 705. We'll have values that are closer to 0.03 and so on and so forth down here, okay? And so, I don't know where this is located, maybe 430 and 480. Let's see if we can kind of find a brighter area, right? 430, the row 480 to 485. 430 to 435, let's see. Yeah, pretty much higher values, 0.88, I think, reflecting kind of this brighter area in the river here, okay? Kind of the reflection there. Okay, so anyway, you just imagine this very big kind of matrix with 720 rows, 890 columns here. And what we want to do is we're going to do PCA, right? We're going to try to take the number of columns which we have, which is currently 899, and can we reduce it to a smaller number of columns? So to do PCA, what we'll do is we will subtract the means off of each column, okay? So I'm going to calculate the means of the columns. So Adam's means, there's 899 values, one average for each column. And all of these things is, I don't know, I guess certain columns of values are a little bit brighter than others, but we do that, and what I'm going to do is I'm going to subtract that off from each column. All right, so now I have my centered matrix, and I can kind of just verify, all right, after I centered the matrix, are all of those things pretty much 0, okay? So it looks like they are. We're getting something on the order of 10 to the minus 18 for all of these things. And so I'm going to just say, are they all equal to something around 0? And I get a true there, okay? And if I were to plot this, what is the effect of subtracting the column means off of our image? What is that going to do? Like, as far as what does an image look like after you subtract the column means? So what happens is we end up getting these, I don't know if you can tell, we get these kind of vertical stripes in our thing, and it's a little bit hard to tell, okay? But we get these vertical streaks because what we're doing is we're subtracting off the column mean. So it's going to affect basically columns, okay? So vertical kind of lines here. And so here is the kind of original image, right? And so if you look at this particular column, there's kind of a lot of bright in this. Like if you look at one column of pixels, there are a lot of brighter pixels in this column. So its average is going to be higher. And so when you subtract off the average, it's going to end up darker. Whereas over here, we have kind of I mean, there's a few bright pixels up here, but overall there's a lot of darkness over here. And so kind of when we subtract off the average here, the average of this column is on the darker side. So we're subtracting off less. So this is going to have the kind of the effect of brightening it, okay? So what we have is this side gets brightened. I guess, yeah, this stuff over here also gets brightened, whereas like this stuff kind of over here, you know, ends up a little bit darker. I don't know if you can kind of see what's happening between this. It's not dramatic, but that's what we're seeing. Okay. So anyway, we've now centered our data. We are going to take our centered data matrix and calculate the covariance matrix. Okay. So the dimensions of our covariance matrix. What will the dimensions of our covariance matrix be? Our original data is 720 rows, 899 columns. So my covariance matrix will be number of columns, right? So it's going to be 899 by 899, okay? So my covariance matrix actually has more values than the original data itself, okay? And then we're going to calculate the eigenvalues and eigenvectors, okay? And technically we're going to have 899 eigenvalues and then 899 eigenvectors, each of length 899, okay? And so if I look at the structure here, we can see 899 eigenvalues, and then I've got 899 eigenvectors, each one of length 899, because we're calculating the eigenvalues and eigenvectors of this basically, yeah, 900 by 900 or 899 by 899 matrix here. Okay, so what I can do is I can say, you know what, let's just keep the first 50 columns, okay, the first 50 eigenvectors. All right, and so PC50, the dimensions of this, now I have 50 eigenvectors, each one of length 899, okay? And I can take my image here and multiply it. So this centered image is 799, right? The dimensions of our image is 720 by 899. I can multiply it by 899 by 50, and so our data is now 720 by 50. Okay, so we've reduced kind of the amount of data that we have to store, right? So 720 by 50 is what, 36,000 values, versus the original thing was, you know, close to 649,000. 720 versus 720 times 899, so, you know, around 65,000 versus 36,000. So so we have that. And okay, if I were to plot this though, okay, 720 by 50 pixels, this is not, it's completely kind of worthless, okay? Because we will not be able to make any sense of it, okay? As.cimg transpose of kind of my projected, okay? Because this is going to show us 720 pixels, or 720 rows by 50 columns, okay? But this is not, this doesn't resemble this at all, right? And really, the bulk of the information is in the first kind of just few eigenvectors, okay? And we just see a whole bunch of gray here, kind of indicating that there's not a ton of information there, and then like kind of the most dramatic information is in like the first left few pixels. So, you know, what what do we want to do? Okay, so the idea here is you would transport, okay, So rather than trying to send 650,000 values, you would just send 36,000 values, okay? And then along with basically instructions to undo this kind of transformation, to go from the 36,000 values back to 650,000 values, okay? So it's kind of like, and you're going to lose information when you do this, right? So it's kind of, so you can report your verbal and your math SAT score, right? So let's say, I don't know, let's say your total SAT is, I don't know, 1,400, right? And so you can tell somebody, my total SAT was 1,400. And then if that person had to then guess, right? And then you say, okay, now reconstruct kind of the two scores, verbal and math. They're not going to get it right, but probably they would just say, okay, well, if your total score is 1,400, let's guess 700 and 700, right? Now your true scores could have been like 800, 600, 600, 800, or 700, 700. Who knows? Who knows what it could have been? But if you say, okay, my total score was 1,400, and then that's what you're going to have that, right? And so basically you're only transporting the smaller quantity, and once we receive the smaller quantities, we're going to then try to expand back out to the full I guess matrix of values, okay? And so to kind of undo our reduction in data, right? So our reduced data is 720 by 50. What we're going to do is we are going to multiply it by the transpose of the 50 eigenvectors that we kept, right? So the 50 eigenvectors that we kept was 899 by 50. So what we're going to do is we're going to transpose this, and so we'll do 720 by 50 times 50 by 899, okay? And so this is going to be kind of our reconstruction, okay? So Adam's REC is going to be kind of our reconstructed data. This is going to be 720 by 899. Okay, so we transported the smaller thing along with kind of this thing. So I guess we're going to have to transport two smaller matrices, and with our two smaller matrices, we can reconstruct the one bigger matrix. Okay, and then we can see, all right, well, what does our image look like? And let me just delete this, okay, and delete this also, just so you can kind of see. So this was our original image. And what I'm going to do is I'm going to plot my reconstructed image. We have to add back kind of the column means, okay? And this is what the reconstructed image looks like, okay? So our original image looks like this. After keeping only 50 of the eigenvectors, okay, reducing it down from 6. So the full 650,000 pixels look like this. If I reduce it down to a column, to basically 720 by 50, transport that, and then say reconstruct it, this is what we get. So we do get, loss of image quality, right? So if you look at the original image and you look at this image, this image is blurrier. There's, kind of, it looks like the forest has gotten smeared over here, right? So you lose a lot of kind of the details of the forest, but overall, if you stepped back, I don't know if you would notice a huge difference between the two images. Okay, so this is kind of a little bit of almost like image compression. This is not how image compression works. This is a very computationally expensive way to do image compression, and so when you use like JPEGs and stuff, that's image compression, and we've probably seen some bad JPEGs where you lost a lot of information and whatnot, and they use a different kind of technique. I think wavelets or something. I don't quite know how a JPEG works. But anyway, this could work as image compression. It's not. It's computationally a little bit too expensive to for it to be practical. Okay. But anyway, I thought that was a little bit neat, and and I wanted to kind of go through and just show like what it looks like to just keep. What if we kept only one eigenvector, right? And then what if we kept two, and all the way up through? So I did a whole bunch of different kind of components. So I guess you can think of like, when you do PCA, principal components analysis, and you have 899 columns, you'll technically have up to 899 principal components, and you can, and in this example, we kept 50 of them. And here I thought, okay, well, what if we kept just one, or what if we kept two, or things like that? So I ran a kind of a big loop. So I'm going to do 1 through 10, and then 12 counting up by 2s, 12, 14, 16, 18, 20, then counting up by 5s, 25, 35, 25, 30, 35, 40, and then maybe counting up by 10s or 20s. So then 50, 70, 90, 120, 150, up to, say, 500 principal components. And then for each of these things, I'm going to just keep the first k principal components. We're going to reconstruct them, and then I'm going to just output as a PNG file. All right, so I'll go ahead and I'll run this. Okay, so I think it ran and it generated a whole bunch of these principal component things. But why don't I just show you kind of our first one. So if I keep only one principal component, this is, you know what, let me delete this. Okay, so here's the original image, okay? And then we said just keep one principal component. So basically, we've taken all 65,000 pixels in this thing, and we said every pixel is just put on kind of this scale from bright to low, and if you do that, this is kind of just the pattern that it generates. Okay, it kind of captures, okay, dark over here, bright over here, something in between over there. Okay, what do we have when we do two PCA, two principal components? Okay, so adding a second principal component, we get a bit more detail in the image, but not much, right? You still have no idea what any of this is. Okay, here we're going to add a third principal component. Okay, and so it's trying to kind of add a bit of structure. So again, the original image looks like this. So there it is with 3. Here's the fourth principal component. Okay, and then maybe, at what point would you be able to kind of recognize? So here, as we kind of add more, keep more principal components, you get a little bit more structure in the image, right? So 6, 5, 4, 3, 2, 1. I don't know. It's kind of fun for me looking at this. So there it is with 7. Okay, 8 principal components. I don't know if we can tell what this is, but a little bit you start to see, it's retaining quite a bit of the structure of the original image, right? So, comparing this with the original thing, it looks like that. Oh, okay, so that's with 10, and then so I didn't actually draw 11, but this is it with 11. And so anyway, we can kind of, I think I can skip through a bunch of these things. Okay. Oh, these are small, but okay. But here it is with 1, 2. All right. I don't know why does it take 10, 12, 14, 16, 18. I don't know. At what point do you feel like we're not getting anything? All right. Okay, original image. Okay, so sorry, it's going to be small here. Okay, so there it is with 1, 2, 3, 4, 5, 6, 7. All right, you guys can count 8, 9, 10, and then 12, 14, 16, 18, 20, 25, 30, 35. Here it is with 40, 35, 40, 50, 70, 90, 120, 150. I mean, I feel like at this point it looks like the original image, and I don't know if there's anything changing from like 210. Like, I'm kind of hard pressed to see if there's much of a difference between these. Maybe a slight increase in contrast. A little bit, right? Okay. And then back here we get a little bit more, it becomes a little bit fuzzier, right? So this was like 40 and 50, and we can see, we get more clarity and more sharpness, and then as we increase this further, we actually get a tiny bit more kind of contrast in our image. Which actually makes sense, because what is contrast in an image? Contrast is kind of the how different are the brights from the darks, right? How bright are the white parts of the image? How dark are the kind of black parts of the image? And so, how bright are the bright parts and how dark are the darks? And if, I guess, an image with high contrast, or, like when you're shopping for a television screen or something, and they talk about this has like really great contrast, it's the idea that like the dark parts are really dark, right? Projection screens don't have great contrast because this part of the screen is supposed to represent the darkest parts of the image. And it's actually like, if I turn the lights up, we would generally say this is white, right? But when but I guess in comparison to this part is white and this part is black. But we also recognize like there's a like real darkness would be like over here, right? So projection screens actually don't have a ton of contrast. But anyway, a television that advertises high contrast is like the bright areas of the screen get really bright, the dark parts of the screen remain really dark. And anyway, when we do something like this and we increase the number of principal components, we see like higher contrast in this. So I guess I can do just kind of 500, keeping 500 principal components, versus keeping 200 principal components. Okay, so as far as like the detail between 200 and 500, we're not getting a ton of change in the detail but I would say more contrast in the image. Okay, so with 500 principal components, the darks and the brights have a greater difference. With 200, they're a little bit closer, and that kind of it gets to the sense of capturing variation, right? So variation in an image, or at least in a black and white image, is kind of like how different are your numbers, how different are the high numbers from the low numbers, and things like that. And so so by increasing the number of principal components, we are able to capture more of that variation. We're able to capture a little bit more of that kind of contrast between the bright areas and the dark areas of the image. But as in order to kind of go from this to this, okay, we had to more than double the amount of information that we have to kind of store. We're storing 200 columns of values to 500 columns of values, and how much are we gaining? I don't know. And again, this is kind of the problem in statistics is how many additional variables do you want to keep, right? So here we go. If I go down to 100 things, okay. So in terms of half the so 100, 200, and 500, there's actually a little bit of kind of blurriness in the 100 PCA versus 200 PCA. But yeah, I don't know. Maybe it's worth cutting it down to 100, or maybe it's worth cutting it down to 50. And I guess it depends on kind of what it is that you're going for. But again, this is not necessarily. We wouldn't actually do image compression using principal components analysis. This kind of just isn't a really practical way to go about doing it. But it does give you a sense of a little bit in terms of you can still kind of capture a lot of the information in a particular data set. But even if you reduce kind of the number of kind of dimensions from something high, if you have a big data set with close to 900 dimensions, chances are some of those variables are going to be correlated, and you can reduce from, say, 900 down to maybe 100 dimensions or 50 dimensions and still manage to capture a high amount of the variation, still capture a lot of the kind of internal structure of the data without necessarily without losing too much information there. Okay, I guess that's about it as far as it's just kind of like a little demo here in terms of I thought it was kind of a neat thing doing PCA in this role. But again, yeah, it's I guess back in the day when computers were a lot slower, this step of calculating all of your eigenvectors would be a little bit too computationally expensive, I think, for the image compression there. But yeah, you could reduce the amount of info being transferred around. Okay, all right. Well, I guess we'll end early today. I think, yeah, I just have a couple random topics, I guess, to cover this week, but I won't be testing you on it. And I guess I should also cover what I'll put on the final exam. I guess we'll do that on Wednesday. So, okay, little short lecture today. Hope that's all right. Thanks for coming, and we'll see you Wednesday, Friday. All right. Okay. All right. Well, have a good rest of your Monday, and we'll see you guys later.